So let's look back at the example. So we had matrix decomposition. Let's do the same thing for Gauss-Seidel. So Gauss-Seidel. What I'm going to do is, let's see, I'll just kind of write out, well, the objective of Gauss-Seidel is we need to have an explicit equation for a given temperature using only on the right-hand side guess temperatures. So another way to say it is I need to solve this entire equation for Ti. And then any place that temperatures appear on the right-hand side, those had better be guessed temperatures, or temperatures that I've already computed in my for loop. Right, so the Gauss-Seidel approach would be something like the following, where we say, I'm going to solve this entire equation. I end up with Ti is equal to, there's a big mess of stuff here. So it's rho e, which is a function of Ti, but that's T hat I, right? And then delta x over AC, I squared, plus Ti minus 1. So I've already maybe computed temperature at this point, so I could either use the hat, T hat I minus 1, or just Ti minus 1. Let's, for the sake of consistency, do T hat I minus 1. And then we have, that's times our conductivity, which is at T hat I minus 1 plus T hat I over 2 times AC over delta x. All right. And then, sorry, I'm running into my other stuff here. Let me just move this BI out of the way. All right, then we have our Ti plus 1. So T hat I plus 1 times K, T hat I plus 1 plus T hat I divided by 2 times AC over delta x. Right, and then all of that's divided by the stuff that was multiplying Ti, right, which is what, K times T hat I minus 1 plus T hat I over 2 times AC over delta x, plus K is a function of T hat I plus 1 plus T hat I over 2 times AC over delta x. Okay. For I equals 2 to n minus 1. Right, so we've achieved our goal, which is I need an expression I can evaluate for Ti. We know that it's going to be a function of some guesses, which we'll update as we go through this. So let's look back at the that example. These are now new. These didn't exist before a couple days ago, so somehow I missed converting these as well. This is the original Gauss-Seidel iteration that we had done, right? We have our error intolerance. Nothing here is temperature dependent. So let's look at what happens when we add the temperature dependence. Again, we define our temperature dependent functions. We go through, we're doing our loop, but you'll notice a few things here. First, we're going to, every iteration, we kind of start over in terms of setting up our new temperature. Right? We'll eventually guess this. But yeah, we'll update our guesses here, but we're just creating a new temperature matrix that we're solving for. Now, for every single node, we go through and substitute out our function, making sure you get the indices right. But it's basically the same thing as before, right? We're just swapping out our functions, making sure we use our guess values on the right-hand side. Compute the error, update the guess, and then let it iterate. So let's see if this one solves. Let's see, actually, probably have the same typo up here, don't I? I minus 1. Anything else? I think that's good. All right. So that messed it up somehow. Yep, thank you. All right. So this approach now takes almost 1,000 iterations. So it's a little bit less computationally efficient than the other one. But it still solves, right? And it's kind of like, it's another tool that you can use. If, for some reason you don't want to do the matrix inversion or it's just too hard to do that, this is a way to deal with it. You should get the same solution here. Questions on Gauss-Seidel? Okay. All right. Let's see where we are. All right, so that's going to wrap up the kind of introduction to our numerical techniques for temperature-dependent properties. We're going to continue using the numerical techniques throughout the semester. We'll talk more about them, and we'll extend on like other methods that you can use that aren't just these two, especially when you get to like non-steady state problems, that kind of thing. But now what we're going to do is we're going to move on in the last 20 minutes here to a new topic, and that is extended surfaces.